All right, ladies and gentlemen, in this lesson, we're going to start by looking at our function from the previous lesson. So remember, this was a function about riding your bike into the wind. And as you get close to 20 miles per hour of wind, the time it takes you to get anywhere goes up and up and up and up, right? We're going to answer some questions about this function in order to investigate these ideas of asymptotes and wholes of rational functions. So the domain of our function, just our general function, we're not going to worry about the context for this, would be, of course, negative infinity to 20, and then 20 to infinity. And we've already actually run into these types of functions when we were studying domain in depth, right? And the feature that gives this function this domain is it has what we're going to call an asymptote. And specifically, it's a vertical asymptote. Okay, so we introduced this term in the last lesson, but the vertical asymptote, of course, refers to this kind of imaginary line that the graph kind of snuggles up to but doesn't actually touch. The reason this is here, you already know this, the reason this is here is that we can't plug x equals 20 into this denominator, right? So x equals 20, it makes the denominator undefined, it makes the denominator 0, so the function is undefined. And we can use these to model a lot of different things, but in our context, remember, we were riding bikes, right? And specifically, we were trying to ride at a 20 mile per hour pace into a 20 mile per hour wind. So that kind of cancels out all of our speed, right? So we aren't moving. And it takes an infinite amount of time to get anywhere, we could say. That doesn't really even make sense, right? But you're never going to get where you're going. So this time gets bigger and bigger and bigger. We could say the limit is infinity, right? So that's the type of situation that these asymptotes are useful to model. Let's define our term, and then we'll look at a slightly different case. So we want to call this a line that the graph approaches. It doesn't touch it, right? It just approaches it as x or y gets close to infinity. So in this case, we're just worried about our vertical asymptote. So that's a y value approaching infinity. But notice there's another asymptote in this graph that we're going to study a bit later. Okay, so we found our vertical asymptote. We notice that it's when the denominator equals 0. Let's look at a more complicated example that we studied. So remember what we did with this one when we were looking at intercepts is we factored it, and we got something like this, right? So we factored the difference of squares on top, and on the bottom, we factored it to this, right? And then we canceled out this term, and we could say that the function is sort of equivalent to x minus 9 over x plus 10, right? For this function, my denominator is x plus 10. If I want that to be equal to 0, that's equal to 0 when x equals negative 10. So what I would guess that this graph would look like would be similar to what we saw before, right? So this time my asymptote is going to be at negative 10. I'll just kind of sketch that in. Notice I'm not really using the grid. I'm just drawing a sketch. I'm going to label it as x equals negative 10 as my asymptote. And I think I had a negative y-intercept. The graph looks something like this, right? So here's my vertical asymptote at x equals negative 10. So here's the trick now. Is this denominator has another 0, and that 0 is when x equals negative 9 from this factor, right? So we definitely have another discontinuity in this graph that we're not seeing. Look at the graph on my calculator. I definitely only see one asymptote. There's not a second asymptote at x equals negative 9. But when I type in, plugging in negative 9 into the function of my calculator, I get to divide by 0. When I look at the table on my calculator of my function, when I go to negative 9, I get an error just like negative 10. But the graph clearly has only one asymptote. So we need to figure out how to represent that there's a discontinuity also at negative 9. The way we're going to represent that is we're going to find negative 9, and we're going to draw an open circle on our graph. And we often just call this a hole at equals negative 9. You can also call it a removable discontinuity. It's a little more academic sounding than a hole. But that's exactly what it is. It's a little spot in the graph that we cannot graph because it makes the fraction, the denominator of the fraction, equal to 0. And what we're representing is that the graph is undefined there. Notice, though, this is like kind of a point, right? So this definitely has a y-coordinate that goes with it. So it's at negative 9 comma something, and we want to figure out what that something is. Well, to do that, we're going to take this, right? And we're going to plug in negative 9 minus 9 over negative 9 plus 10. And what do we get? Negative 18 over 1 is negative 18. So that's the y value that goes with that whole. So the function approaches that value from both sides, but doesn't touch it, skips over that because it makes the denominator equal to 0. So the relationship here of these features is that vertical asymptotes occur at zeros of the denominator whose factors do not cancel. So x plus 10 was left over. Wholes occur at zeros of the denominator whose factors do cancel. Okay? So now you are empowered to find both of these. So these are both discontinuities that we'd see in our rational functions. They both affect the domain of our rational functions. The only difference, right, is that the vertical asymptote is this whole line that the function skips, whereas this whole is just a little spot it jumps over, and it has a y value that goes with it. And it's good to make yourself this note of finding that y value if you think that will be helpful for you. And it comes from, of course, the simplified version of the function.